Part 2 involves the tabular method, where we use repeated integration by parts. And when we do that, what we are really looking is for our choice of u to go to du's that eventually go to 0 or knock out entirely. And that's the moment that our integration by parts ends. So let's do an example like this. Let's say that we have the integral of x to the third e to the x dx. Now, if I do a U-substitution of this and say, or do an integration by parts and say that u is equal to x cubed, since it's a polynomial function, it gets prioritized over the exponential. We go du is 3x squared dx. dv would be equal to e to the x dx. And v is equal to e to the x. I'm not going to actually write this out. I want you to see that we're going to get the integral of this, which is then going to require us to do another one where u is equal to x cubed, or 3x squared, and then another one where it's an x term, and then another one. So what you're going to have is a uv minus an integral that becomes another uv minus another integral that becomes another uv minus that, and so on. You're just going to kind of keep repeating that process over and over until you kind of end up with a du that's 0, and you can finally finish it. The other thing that happens is if you look at these signs, you have uv minus uv, but then plus this one, but then minus that one. So you have an alternating sign thing. Well, we can simplify that greatly by using a method called the tabular method, where we're going to just build a table, and on one side of the table we're going to put our u, and we're going to go down from our choice of u and keep differentiating, and on the other side we're going to pick our dv, and we're going to keep going upwards, and we're going to integrate. So we're going to do the same choice that we did before. U is going to be x to the third, dv is going to be e to the x, and as I move down the table with my x to the third, I get 3x squared, then 6x, then 6, and then 0. And of course, as I move down with e to the x, I actually just get e to the x, e to the x, e to the x, e to the x. So what we are going to now assign is just kind of the the u and the dv go together, because this was a v, so this was a dv, this was a v, and I'm going to kind of cross those, and I know that that's going to be positive. But then I'm going to subtract the next one, because that would be the minus integral of v du, but that's actually split up again. So what we end up having is this alternating sign thing, and if we match terms like this, it's not too hard to prove that this ends up being x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 e to the x, and then don't forget your plus c. Again, the proof of this is just going to be working through the integration by parts step by step and watching this alternating sign thing happen, and watching as you keep differentiating u further while the integral of e to the x stays the same. So this is a much quicker way to do repeated differentiation by parts. Let's do another example. Let's go the integral of x to the third sine of 4x dx. So it's not quite as simple as the one we just did, although it's very similar. If I do a table and I say that this is going to be x to the third, and then I'm going to put sine of 4x as my other term, then as I move down the table, again we have 3x squared, 6x, 6, and 0. Remember, this integrals of trig functions just cycle through every 4, but we also have this 4x to be aware of. So this is going to become negative 1/4 cosine of 4x. Then the integral of cosine is sine, so this is going to become negative, divide by 4, 1/16 sine of 4x. Then this is going to cycle back to become positive, divide by 4 again, 1/64 cosine of 4x. Then finally we get 1, so 64 times 4 is 128, 256. Sine of 4x. Plus, minus, plus, minus, plus. And 1, 2, 3, 4 linkages to create. So our integral is going to be negative x cubed cosine 4x over 4 plus 3x squared sine of 4x over 16. Then I'm going to have, let's see, this is going to be plus, so that's plus, minus, that's minus, this is going to be plus. I can simplify the 6 and the 64 to give me 3x cosine 4x over 32, and then minus, this would be 3 sine of 4x over 128, and then plus c. And that's the whole huge integral. So that's the tabular method. You guys are going to have some fun with that. Let's do a few more examples with that, one that uses a definite integral. So we're going to do the integral from 0 to pi over 8 of the x times secant squared of 2x dx. So again, tabular method. I have an x, so that becomes x, 1, and then 0. Secant squared of 2x. I can take that a few steps. I know that the integral of secant squared is tangent, so this is going to give me 1/2 times the tangent of 2x. And then I know the integral of tangent is the negative natural log of the cosine, so dividing by 4 and making negative 1/4 natural log of the cosine of 2x. So we build our integral using plus, minus. So this was only 2 steps, but it still saved time without having to worry about u and v's. So I get x over 2 tangent of 2x plus 1/4 natural log of the cosine of 2x. And that's going to be evaluated from 0 to pi over 8. So when I plug pi over 8 in, I get pi over 16 times the tangent of pi over 4 plus 1/4 times the natural log of, this would be the cosine of pi over 4 minus, well, the tangent of 0, well, 0 over 2 is 0, so that doesn't matter. And then the cosine of 0 is 1, but the natural log of 1 is 0. So those are out. Tangent of pi over 4 is 1, so I get pi over 16 plus 1/4 natural log of, and the cosine of pi over 4 is 1 over root 2, or root 2 over 2. This is pi over 16. Let's use our log rules to kind of simplify that log expression. This is really 2 to the negative 1/2, so negative 1/2 natural log of 2. And I can simplify that to pi over 16 minus the natural log of 2 divided by 8. Okay. Let's do another example. This is going to be an indefinite integral, the integral of secant cubed x dx. This is a difficult one to kind of start if you don't have an idea of where to go, but we want to show you several examples so you can kind of recognize these when you see them. If I separate this by parts, I'm really going to want to separate it into a secant of x, which I know how to take a derivative of, and a secant squared x, which I know how to take an integral of. So I get u is equal to secant x, du is secant x tangent x, and if I say that dv is equal to secant squared x dx, then v would be equal to the tangent of x. So setting up my integral, I'm going to get uv, so secant x tangent x, minus the integral of v to u would be secant x tangent squared x dx. Well, let's keep going. Secant x tangent x minus, and I could try a U-substitution here again, but why don't we get everything in terms of secants first? Because I know that the 1 plus tangent squared x equals secant squared x. So I can convert tangents into secants, and if I do that, I get secant squared x minus 1 dx. Keep going. Secant x tangent x minus, I can actually keep this integral as and make this the secant cubed x minus the secant of x dx. So splitting this integral up now into two different integrals gives me the negative integral of secant cubed x dx plus the integral of the secant of x dx. And if you guys remember what we did yesterday, when I have the integral of the secant cubed x dx equal to all that, I'm kind of back to a point where I have the same thing, and I can add that to both sides, giving me 2 times the integral of secant cubed x dx equals secant x tangent x. And then the integral of secant is one of those that you just have to remember. I wrote it off to the side, but I'll let you do that. It's the natural log of the absolute value of the secant of x plus the tangent of x, and plus c. Dividing both sides by 2, and I get the integral of secant cubed x dx equals 1/2 times the secant of x tangent x plus 1/2 times the natural log of the secant of x plus the tangent of x plus a constant, and I'm going to recall this constant C1 because I just have a new one, and that's my integral, and we're done.